In order to combat climate change and preserve the environment, the European Commission has implemented a strategy. This strategy is largely implemented by the Green Deal, one of whose objectives is to achieve a zero-carbon target by 2050. The aim is to save energy through greater efficiency, implementing a circular economy, improving our waste collection, and ensuring a circularity of raw materials and consumer goods, especially those that include plastics. Each year in Europe, more than 50 million tons of plastic are used for economic activities. This represents 25 million tons of waste, of which only 30% is collected for recycling. Even though waste management and recycling are improving significantly in the EU, the majority of plastic waste is still disposed of in landfills or incinerated. We are therefore still a long way from a circular economy. While 40% of plastics used in Europe are packaging plastics, some of the biggest producers and consumers of plastics are the automotive industry and electrical and electronic equipment. These alone account for 15% of total plastic consumption. Therefore, addressing this sector as a priority can be a real breakthrough. The circular economy is expected to contribute to achieving a significant part of the European Green Deal, so it is essential to push forward research in this area. This is the objective of the European research project PlasPLus, which has brought together several players from the research sector, the plastics and the automotive industries, and the recycling sector. The first axis of PlasPLus is tackling the demonstration at industrial level of the separation of a complex mixture of plastics from automotive shredder residues and WEEE. More specifically, 3 plastics of the same density: ABS, PS and filled PP. These 3 plastics are automotive industry favorites. In addition, given their lightweight, plastics will increasingly be used in electric vehicles, all the more reason given the energy transition to optimize their recycling.
Nous voulons aller toujours de l'avant et donc recycler toujours plus, c'est-à-dire d'aller chercher des plastiques de plus haute pureté. Donc nous avons dû développer un procédé pour purifier et séparer la fraction PP chargé que nous appelons chez Comet le PP chargé. Dans le cadre de PlasPLus, notre procédé sépare le PP chargé de 2 autres matières que sont l'ABS et le PS. Nous utilisons différentes techniques de séparation, dont la séparation triboélectrique que nous avons adaptée à ce mélange ternaire de plastique. La triboélectricité classique ne sait séparer que des mélanges binaires. Nous l'avons adapté pour arriver à atteindre des taux de pureté supérieurs à 98% sur le PP chargé.
We are glad you stepped into this FPP project, which was complicated in the past, but now you managed to deal with it, and for us it is feedstock. And we use it as feedstock to be a new feedstock again, a very sustainable version of the fossil-based version. We use it for all kinds of applications. It can go into automotive, it can go into packaging, it can go in even in garden furniture.
I'm very glad to see that within this project there's actual interest by OEMs, automotive manufacturers, in the use of the recyclate generated from the automotive recycling.
In PlasPLus project we want to create a new standard, a new material that today is not yet available. Clearly we have already in our standard some material that belongs to the recycled content, but for sure we don't have any material that belongs to the end-of-life post-shredding solution, and we don't have any ABS or any type of PC-ABS coming from this feedstock in our standard. Our goal at the end in 2038 will be to have a zero carbon footprint emission in the production of our vehicle.
Il mio ruolo in PlasPLus è creare nuovi compound da materiali rigenerati provenienti da un partner che è nominato Comet. Quindi dall'arrivo di materie prime come polipropilene rigenerato e ABS abbiamo creato dei nuovi compound per applicazioni sia nell'automotive che nel settore elettrico ed elettronico. Il nostro obiettivo è creare il maggior numero di compound che contengano dal 70 al 100% di materia rigenerata.
Ici, nous sommes dans un projet qui ne fait pas de downcycling, mais du upcycling. C'est-à-dire que nous partons d'un déchet, typiquement ici un véhicule hors d'usage, et nous reproduisons une matière première qui va être utilisé pour refaire des pièces automobiles.
The major challenge was to meet car manufacturers' specifications and build a part with at least 40% recycled plastic. During the first tests, the mixture made within the framework of PlasPLus made it possible to achieve a rate of 100% recycled materials for the construction of an interior part. The second axis of PlasPLus is on plastics containing additives that give them different properties. These include antimony, whose basic attribute is to act as a synergist to provide flame retardancy properties. The main challenge in making vehicles, coffee makers, vacuum cleaners and computers is that they need plastics with specific properties. They must be resistant to deformation, fire or temperature variations while maintaining their shape. This range of requirements explains why there are dozens of different plastics on the market and therefore also in our waste. Some of these plastics contain environmentally harmful additives, such as bromine, which are now banned internationally, making them difficult to recycle. They also contain rare additives that are useful to preserve, such as antimony, which is recognized as a critical raw material by the European Commission.
Antimony is a critical raw material for Europe. It is only coming from certain sources like Russia, China, Bolivia, and in some cases also Canada.
Because of the diversity of electronic devices being discarded, different types of plastics are also mixed together. The aim is to separate them and then be able to remove the antimony or bromine for reuse.
And how do we do that? With the flame retardant plastics, we go to the pyrolysis. The pyrolysis consists in heating the material at high temperature and without oxygen. In that conditions, a fraction of the plastic will be evaporated and the vapor after condensation will produce an oil. And the fraction of the material which was not vaporized will be transformed into a black powder that we call char. And the pyrolysis process is interesting because if you burn the oil produced by the pyrolysis, you have enough energy so that the process can be energetically self-sufficient.
The role of the university is to deal with the antimony char coming from the pyrolysis. Here, of course, we have antimony, and our first job was to do a detailed characterization, to know how much antimony we have in it, of course, but also to know all the impurities that we have in it, because all these impurities will have an impact on the downstream process. After the detailed characterization of the antimony char, we deal with the hydrometallurgical process. We have two main steps: the antimony leaching and after the antimony precipitation.
Leaching is a process that transforms partially the char provided by Comet into a liquid solution. This liquid is then precipitated into an antimony compound that returns to the antimony industry.
After the antimony is melted, air injection causes an exothermal reaction, which causes the formation of antimony gases. In our cooling process, the antimony gases are formed into a fine white powder, antimony trioxide. This product is then later packed in bags or small bags or goes directly into our extrusion department. There we bring some additives into a plastic carrier to make a flame retardant master batch that we can deliver to our customers.
The antimony component is a very interesting one. So it's very good to have a party looking actively into recovering this valuable material, which can serve a new life, either as a new role as a synergist for certain flame retardants or other antimony-related purposes.
In exploring different technologies for separating plastics containing flame retardants, a technology from the University of Liège has proven to be particularly effective in separating plastics from electronic printed circuit boards. This is an additional achievement in the framework of PlasPLus that will certainly be used to improve the recycling of electronic components.
We developed a multi-sensor solution. We investigated the possibility of using LIPS, which stands for laser-induced breakdown spectroscopy. So we are shooting the pieces with a laser in order to detect whether or not the plastics contain flame retardant materials. During the project, we also realized that an additional constraint happened. We needed to extract printed circuit board out of the flow of materials because it contaminated the flow of the material. And we developed a custom software to detect those printed circuit board which are then extracted by the robot.
The PlasPLus project is therefore a real success. First of all, it has made possible the development of promising technologies that will revolutionize the circular economy in the automotive sector by allowing plastics such as ABS, PP and PS to be reused with properties identical to petroleum-based raw materials. But it has also enabled the development of an unprecedented antimony recycling process. These new sorting technologies will help the recycling and plastics producing sectors to better achieve the environmental objectives of the automotive and electronics industries and together move forward towards a zero-carbon European industry.